Hi, Ali.
Hi.
Another one. Hello, Karen. All right, it's 9:30, folks. Good morning. Thanks for coming. All right, so I know that some people logged in on Monday. I had sent an email saying there wasn't going to be a Zoom class on Monday. So I hope that got sorted out. You didn't think I was just flaking on you. So we pretty much did get through everything we needed to get through for test 3. So let's see where we're at in the syllabus. And you can see we're at the week of 1026 here. And we have gone through all these topics that are required for test 3, and test 3 is going to be due on Monday. So there won't be a class on Monday because that's when test 3 is due. Now, a grand total of 1 person has taken test 3 at this juncture, and I want to remind you, you don't have to wait until the day of test 3 in order to take test 3. You can take it before then if you'd like. In fact, I'd recommend it. The extra credit will close at 11:59 p.m. on Sunday evening. I would recommend taking the test before then so you can judge how much extra credit you might need to do to get the grade that you want, because the extra credit gets added to your test score per what's in the syllabus. So it adds up all the total extra credit you've got from those quizzes, divides it by 2, and that's what gets added to your test score. It's a total of 6.5 points, I think, that you can possibly get. Does anybody have any questions right now about where we are in the course or anything else at this point? There have been 7 total attempts at the practice test, which isn't very encouraging. I was kind of hoping that since we had finished all of the material that people would get into studying it, but it seems like it's going to be a last minute deal again, which hasn't been very successful for a lot of you. So I'm hoping that, well, you know what Einstein said? He said, you know, the definition of insanity is doing the same thing over and over and hoping for a different result. So, you know, waiting for the last minute doesn't seem to be working for some people. I don't understand why they would continue doing it. I don't understand a lot of things, but that's something that really gets to me here. I don't have any control over that. I can't make you study. All right, let's go through the practice test. Now I want you to remember, with regard to the practice test, let's go back to that. Sorry. Go back to the previous page here. There's these videos here, and these videos tell you, well, they give examples for every single problem on that test. And that means that if you're having trouble trying to figure out what I mean, or the wording, or what I'm looking for, then you can watch the video and that will tell you what you'll need to do. So I would strongly recommend going through the practice test and then watching any videos for any questions you're not sure of, especially the word problems, what I'm looking for, what I mean. I think I've been incredibly transparent, especially with the fact that the real test is exactly the same as the practice test. So if you do the practice test enough times, I don't understand how you can fail the real one. But, you know, it's going to be your challenge, I suppose. All right, let's go back to practice test. Does anybody have any questions right now? Christopher, you all right? All right. I had talked last time about the possibility of making people put their video on, but I'm not actually going to enforce it because I feel like I really need to put that in the syllabus from the very beginning. I don't feel like it's going to be valuable to me to try and force this on you now. I still think it's valuable for people to do it because I think it does raise the engagement level. And I think that a lot of you, I'm sorry to say it, a lot of you are half listening to me right now. You're doing something else and you don't want me to know it. So that's why you keep the video off. I really can't think of any other reason. Some people say, well, you know, it's a privacy issue. People don't want to show their bedrooms. They don't want to show where they're at. I think that's all garbage. I think that's my opinion. I think the only reason that people keep their video off is so that they can multitask. Some people are not even at the screen, and I know this because they're left here at the very end, and I say, well, do you need any help? And no answer. So I know they're not even at their computer. You might think I'm taking it too personally, but that's how I feel about it. So I'm not going to enforce it, but just know That's what I'm thinking. Fairly or not fairly, that's what I'm thinking. Okay, so in this first one, we're looking at the enthalpy, and I'll get the, let me get my paintbrush here. And I'm not going to go through these problems completely. I'm just going to give a rough overview of what we're looking at here. Let me see if I can find my menu here. All right. So for the first one, we're looking at the delta H naught, and it's going to be the sum of the delta H naught of formation of the products minus the sum of the delta H of formation of the reactants. And you can see the delta HF naught values, they're all here, they're given to you. You don't have to go hunting for them. The unit is up here as well, kilojoules per mole. That's what you can see there. So you know what to put at the end as far as the unit goes. It's exactly what's here. The unit technically actually could be kilojoules or kilojoules per mole. I think a lot of those are used interchangeably. I think kilojoules is the better unit. Although I don't know if I actually assign any points to the unit, to be completely honest with that. So what that means is, again, I'm not going to do the whole problem. I'm just going to show you how I would set it up. So the products, I would put them into square brackets like this. So 2 times, the products are D, which is 98.17. Plus E, which is 66.52, and that's just 1 times that. So you'll notice I have to multiply by however many I have. And then we subtract, of course, all the reactants from that, which would be 3 times 71.24 plus 5 times negative 5.98. Plus 2 times negative 4.20. The other thing I wouldn't do is do these separately and then come up with significant figures based on what you're seeing here. I mean, I suppose it doesn't matter so much for this one because everything has two places past the decimal. But the answer is going to have 2 places past the decimal as well. So whatever it comes up with, it's going to be 2 places past the decimal.
And the units for this problem would be kilojoules per mole, right?
Well, I think it's kilojoules really, because it's a reaction. And when you say kilojoules per mole of what, would be the question I would ask. Although I would say a lot of people do use kilojoules per mole for this unit. I don't think it's correct myself, but still a lot of people still do it. So I don't think I assign points to it. So I think either would be okay, but in reality, I think kilojoules.
Okay.
Okay.
Thank you.
All right. Any questions about number 1? Now, number 2, this is one I think is especially useful to look at the video for, because it goes through exactly what you're expected to do with it in the video. And I know it's hard when you first look at this to follow the word problem, but if you just take it one step at a time, it's not so bad. Now it says here, it says 8 C atoms joined in a cyclic or circular structure. Now the 2 possibilities that you could have for this problem involve using a cyclic, or there could be one that's straight chain, where it's just a one chain of atoms. And obviously the difference will be whether it says cyclic or straight chain or a chain. So in this case, it's circular. So what you would do is well, since it's 8, you know what that's an octagon. So what I would do is I'd try and draw an octagon of C's is what I would do. And I think that direction is pretty clear in the wording. Okay. That's what I come up with first. So 8 C atoms joined in a cyclic or circular structure. And it says here with as many H's connected so that each C atom has 4 bonds in total. So presently, all of these C's have 2 bonds. So you'll notice they'll all require 2 hydrogens. Actually, what I'll do is I'll just write CH2s next to them. Is anybody unclear about any of this so far? Okay, so we're up to this point here in total. Added to as many O2 atoms as would be required to react to give CO2, and CO2 is C double bonded to 2 oxygen atoms and water. So the reaction looks like this plus O2. Actually, I'll draw that out. Which gives CO2, which is C double bonded to 2 oxygens and H2O. So let me say, I mean, can you imagine looking at this test, not having taken the practice test, seeing this for the first time and not having practiced it? I would, I don't know, that would be annoying, I think. I think it would be devastating, actually. Now you'll notice this isn't balanced, right? So what you'd have to do is you have to balance this first. So it'd be C8, H16, which I will just put in there as the molecular formula, plus CO2 plus H2O. So you'd have an 8 in front of the CO2, you'll have 8 in front of the H2O. And then you'll have, let's see, 8 times 2 is 16 and plus 8 is 24. So it'd be 12O2 for the oxygens. So what I would do is, and yeah, that's completely balanced now. So I would put a 1 in front of here. I'd put, let's see, 12 in front of the O2. I'd have 8 for the CO2 and 8 for the H2O. And then what that allows me to do is come up with all the bonds. So the delta H here is going to be, you'll notice it's going to be different to the one we started with, but it's the sum of the bond energies of the reactants minus the sum of the bond energies of the product. So it's the opposite. Now the reason for that is because the heat of formation is due to formation of bonds, whereas bond energies are about breaking bonds. So it's the opposite way around. So you'll notice it goes for R and P instead of P and R. Does anybody have any questions?
Yeah, I have a question.
Okay. Mm-hmm.
Which unit is this? Is this the what's it called? Enthalpy from bond energy? Is that what you're doing right now?
Yes.
Okay.
But the data is in the question, David.
And for the question, you don't give like a chart like you give on the credit quiz.
No, it's down the bottom of the question.
There's a picture of what the it looks like, or do you have to sort of piece that together in your mind based on?
Well, I don't know. I don't think it's really that big a trial. I mean, if you look down here, it says C single bond C is 347, C single bond H is 414, C double bond O is 736, O double bond O is 498, and O single bond H is 464. That's all the information you need.
All right. Just want to make sure.
I really don't see it as being too bad.
Okay.
All right. So what I would do is I would count up how many bonds I have in total on the reactant side. And I'm looking at it and I have 8 CC single bonds. Oops. And we have 16 by CH bonds. And we have 12 by OO double bond. Running out of room here. I'll just put it, I'll squeeze it in here. So that's all on the reactant side, and then on the product side, we've got 16 by C double bond O, and we've got 16 OH. Nothing cancels out here for this one, so we just have to go with what we've got here. But then we're just multiplying all of the things that we have here. It's just going to be something that has no decimal places in the answer, and it's whatever you come out with. Does anybody have any questions?
So the unit for this would be H?
No, the unit's going to be, we're looking at the data up here, it says kilojoules per mole. So either kilojoules per mole, but I think kilojoules is probably, again, the better unit.
Okay.
The moles kind of cancels because of the number of bonds. They're kind of like moles in their own way because it is balanced. It's a balanced reaction. All right, any questions about number 2?
Yeah, I'm a little bit confused as to how you figured out how to draw that structure. Like, it describes it, but I don't really get the description of that first paragraph. The 8
just tell me what's unclear about. Tell me what's unclear exactly for you.
I don't know. I just have trouble. I have trouble thinking about how much of each different type of bond there is without visually seeing it. So reading it is just a little bit confusing to me. That's all. And I was just,
okay.
I don't know.
All right. So 8 C atoms joined together in a circle. What is
No,
that?
that's not.
Clear? Okay. All
No,
right.
with as many H's connected so that each C atom has 4 bonds in total, added to as many O2 atoms.
Oh, no, just that's the thing. You've got to take it one step at a time. Right?
Okay.
So if you've got, it says 8 C atoms joined in a cyclic circular structure with as many H's connected to it. So each C atom has 4 bonds. I'd stop right there and do that part, right? So what that means is that once you've drawn that circle with the C's in it, you can see that each C has 2 bonds. So each C needs 2 hydrogens in order to make up 4 bonds.
Okay.
That's what that's saying.
All right.
And then you go to the next step. It says added to as many O2 atoms. So we do plus O2 to give CO2 and H2O. And then we have to balance it. And then we can count up all the bonds. So that's the thing, David. You take it one step at a time.
Okay.
And again, when you're practicing these, if it's too difficult to understand the writing here, then you need to watch those videos to show you how to do it, because I do go through all of that in the videos and explain exactly what I mean by those hydrogens and everything else that I'm talking about.
All right.
Okay. Now, the other question you might have is, well, why don't I just draw a picture there? Well, the thing is, my challenge with this course was to make it so it would be accessible. And what that means is that anybody who's blind needs to also be able to see this and be able to do it without me having to describe the pictures. So what I do is I do it in words instead. And that way, a blind person with a screen reader can do exactly what you need to do, and that is, come up with it. But they have to come up with it in their mind, which is a little bit harder. You get to draw it out.
Okay.
All right, so, you know, and obviously these numbers can vary, and it can be different numbers of C atoms, and it could also be straight chain, which is, again, a different kind of problem. All right, any other questions about number 2? Okay, again, take it one step at a time, right? You understand each part and you'll get the whole thing. Oops. There we go. All right, so the next one is Hess's law. So these aren't real compounds, obviously, but you know, the same rules will apply here as apply to any of these other kinds of Hess law problems that you've done, or any of the other examples I've pointed you towards. The idea is that we've got all of these different reactions. We have to find a way to manipulate them, either by flipping them or multiplying them, in order to come up with this final reaction down the bottom here. So you'll see that what you should do is focus on what's in this specific reaction that we're looking for, and make sure that everything's on the correct side. So what I would do is look for D first. Now, I see that D only appears in one of these reactions. It appears in the second one, and it's on the incorrect side. I can look at that and I can see that this is required to be on the left-hand side, but in the reaction we're given it's on the right-hand side. So I know immediately that for the second reaction, I'm going to have to flip it. Actually, I'm going to do this as well. I'm going to say that we can also see it's 2D in the reaction we're given and only 1D in the reaction we want. So I know I'm going to have to divide all this through by 2, which is obviously the same as multiplying by 1/2. And if I do that, I'm going to end up getting with this. I'll end up with 2A plus D gives E plus 2F. And if I look at that delta H value, which is 168, I know that what I have to do with that is change the sign, so it becomes negative 168, and divide that by 2, which becomes negative 84. So we have kilojoules per mole here as our unit, or kilojoules, I think it is actually. I'm lying, kilojoules, there we go. So it'd be negative 84 on reaction 2. Then I look at G, and I see G has a 1 in front of it, and the one we want, and it has a 1 in front of it here. It's on the correct side. What that tells me is that the reaction 3 is correct as it stands. I don't have to do anything with it. And that would be left as 147 kilojoules. Now I have to figure out what I need to do with reaction 1. And I'm hoping you can see that if I left it as it is, there's no way I could cancel out the B and the C and the 2A. But if I flip it and make it B plus C gives 2A, you can see now that that will allow the 2A, the B and the C to cancel. I wouldn't have been able to do that otherwise. So the B and the C can now cancel. You'll notice I've changed the sign of the kilojoules as well. And what does that leave me? Well, the 2F's also cancel as well. And we're left with D plus G. D plus G gives E, and that's it. And then add all these together, and that comes out with my kilojoules for that reaction. Does anybody have any questions about the Hess's law problem here?
So just to be clear, so to flip it, all you need to do is just multiply it by -1, and that doesn't make the coefficients of the the A and the D negative, it just makes the delta H negative, right?
That's right. Yeah.
And then at the end you add them all together.
That's right.
Okay. All right, that's all.
All right. Anybody got any other questions about number 3? Okay. The next one is about Bohr transitions. You'll notice I give you equations here. This is the equation for energy. This one here is the equation that involves the frequency. And this one is the one that involves the wavelength. And again, even if you don't know how to handle ZJ, little zj, I do have the conversion factor for zetajoules in here. But I also, in the video, go through and explain how to apply that into the problem. So the other things you need are also here as well, all of the constant values, so you don't have to remember any of them. And the units are given too, and I think those are very helpful as well in these problems. So we're looking for the energy of the photon, and to do that we're going, and you'll notice we are given the n transitions. So we're going to be using the first equation here for this one's number 4. So it's E, so you don't have to remember it, it's right there, it's right in front of you, 2.179. So I've got E negative 18, that's times 10 to the negative 18 joules. And that'll be times 1 over, now I'd go 2 squared minus 1 over 9 squared. The reason I would do that, why I'd put 2 as N1 and then 9 as N2, is so that I end up with a positive value of E. So after you've done that, you get the value, and that value will of course have a unit of joules. So I do grade on the units for this one, definitely. Does anybody, that's joules, right? So then we need zetajoules, and I would multiply it by 1 zj over 1 times 10 to the negative 21 joules. You'll notice the joules will cancel. I'll be left with zetajoules, and that'll give me my final answer there. All right, does anybody have any questions about number 4?
In that first part of the equation, it's 10 to the negative what?
18.
Okay.
Yeah, you can see it up here, Emily. See it?
Oh, yeah. Okay.
It's E negative 18, which is 10 times 10 to the negative 18.
Okay.
That's always written in regular text, not as a superscript or anything.
Yeah.
It's just like it is in your calculator, really. All right, any questions about number 4?
Yeah. Real quick, for the N1 and the N2, why'd you say that 9 was N2 and 2 was N1? Is that just...
It's so I end up with a positive value for energy.
Okay.
Right, I mean, if I did it the other way around, the result would be the same but negative.
Okay.
But the question's asking for the energy of the photon, not the energy released or anything else. I mean, it's going to be a positive value. Yeah, sorry.
So I came across this problem when I was working on the assignments and everything like that, and it stumped me. So like when it's like there was a problem involving like you had to find out, they gave you the N1 value, and I have to figure out like it transitions down to N1, but I had to find where it started basically. And I got through all the steps and everything like that. Now I'm on the last problem with the E 2179 times 10 to the 18th 1 over n squared minus 1 over 1 squared. And I have no idea how to algebraically solve that. I've never seen, I just don't know how to approach this right now, you know?
Okay, well, you should talk with me privately about that.
All right,
because it is just straight algebra. I'm sorry, it's not even chemistry.
Okay.
To be blunt.
And it's like I think I could figure it out. It's just I just haven't seen the process of solving it yet, and maybe I'm not familiar with it. I don't know.
Like I said, it's just algebra. It's not chemistry at all. But I'm happy to help you with it. Maybe after class.
Too easy.
Okay. All right. Any other questions about number 4? Okay. All right. Number 5, we're looking for the frequency, and that's in terahertz here. Now, again, remember that, yeah, these problems are a little different than what we went over in the PowerPoint. But, you know, if you really don't know exactly what I'm looking for, then you need to go back to my videos and take a look. Okay, the videos here for these questions will tell you exactly what you need to do. Number 5, so we're looking for the frequency here. So in order to get the frequency, according to the equations you're given in the test, is going to be E equals H nu. So we know we're going to have to have energy here first before we find the frequency. So what we do is we apply what we did earlier. So we got the energy, 2.179 times 10 to the negative 18 joules. And in this case, I'll do 1 over 5 squared minus 1 over 14 squared. And that will give me an answer in joules. Now, the other equation I would apply then is my frequency equation. E equals H nu, nu equals E over H, and the E value, which is from here, is in joules, and the H value you're given here is Planck's constant, 6.2626. Times 10 to the negative 34. That's 6. All right, I'll rewrite that. Let's try that again. 6.626 times 10 to the negative 34 joule seconds is Planck's constant. You'll notice the joules cancel here, and we'll end up with seconds to the minus 1 as units, which is the same as Hz or hertz. But we're looking for terahertz, so it would be terahertz is going to be hertz times, and it says here 1 terahertz is the same as 1 times 10 to the 12th hertz. And that will give me my value in terahertz. Does anybody have any questions? Nothing to remember. I mean, it's all the constants and everything given to you. The last one here is wavelength, and it's in nanometers. And you can see again, we're given these energy transitions from n equals 13 to n equals 4. And what we're going to have to do with this is again, do the step that involves finding that energy difference. It'll be 1 over, you'll notice I always put the bigger value, which is 1 over 4 squared over 1 over 13 squared. I mean, I know that 13 is bigger than 4, but 1 over 4 is bigger than 1 over 13, or 1 over 4 squared is bigger than 1 over 13 squared. That's how we're ending up with a positive value for that. So that gives us our energy in joules. We can do our frequency again. So frequency is equal to the E divided by H. which is going to be the energy here that we calculate, divided by the H, which is 6.626 times 10 to the negative 34 joule seconds. That's joules over joule seconds. Again, the joules cancel. We're left with something with seconds to the -1 as the final unit, or hertz, which is the same thing. And the last thing here is the wavelength, and we know that C equals nu lambda. So lambda equals C divided by nu. C is the speed of light, 2.998 times 10 to the 8th meters per second, divided by whatever we get here, seconds to the -1. So you'll notice that that'll cancel, the per seconds will cancel, we're left with meters, and then we need nanometers. So we can do one extra step on top of that, and we see that 1 nanometer is equal to 10 to the negative 9 meters. And that gives us our final result in nanometers. All right, does anybody have any questions about number 6? Write that up here, it's number 6. Any questions? All right, so the next one is about quantum number sets. And I think for this one, it's good to have in your mind what the rules are as regards these quantum numbers and the allowed values. And these are as follows. So we know that for n can be 1, 2, etc. The next one is L, which can be anywhere from 0 up to n minus 1, m sub L, which can be negative L to plus L, and m sub S. Now, if you weren't here when I went through this is going to look incredibly annoying, I suppose. So I'd recommend you go back and watch the class where I talked about it and watch some of the videos. Right, I'm not going to go through and explain all of these values right now. So for this one here, we're looking for whether or not it's valid, and if it's not valid, what the reason for that might be. So I'm looking at n is allowed, n is one of those values. The L can be anything from 0, 1, 2, 3, or 4, according to what I've got on the screen here. So I know that L is okay. M sub L is 5, and that's not allowed because M sub L can only be negative L to plus L, which would be negative 1, 0, or 1. So the answer would be it's invalid because M sub L is out of range. That would be my answer. Does anybody have any questions about number 7? All right, number 8.
What did you get for the answer again?
M sub L, set's invalid. M sub L is out of range.
Okay.
Number 8, n equals 5, that's an allowed value. L equals 2, that's an allowed value. And anything from 0, 1, 2, or 3, or 4 would have been valid for L. M sub L is 0, and that would be valid because the values for M sub L could be negative 2, negative 1, 0, 1, or 2, so negative 2 to plus 2. And M sub S is minus 1/2, and that's allowed. So the answer is that it's valid. That would be a valid set for that one. Does anybody have any questions for number 8?
So just in general, for n sub S, you can't have -1. It's the only options are +1/2 or -1/2.
That's correct.
Okay.
That's it. I mean, that's all electrons are allowed to be. There are other spins possible for other species, but electrons are always plus or minus a half, always.
Okay, thank you.
Question 9, same kind of deal. N equals 1, that's okay. L equals 5, that's not okay. The only possible value for L would have been 0. So if L equals 5 is out of range. So L is out of range. All it takes is just one of these to be invalid and the whole thing is invalid. This one, N equals 4, that's in range. L equals 4, that's out of range. L can only be 0, 1, 2, or 3. You can only go up to N minus 1. So that, again, L would be out of range for that. Does anybody have any questions? Okay. Next one is electron configurations. And for this one, what we're looking at is looking for the diagram that best describes electron configuration of a given element. In this case, it's AR that we're looking at. You'll notice I've got the picture. Below it is a written description of the picture. You can just ignore that. Just look at the picture. My best advice to you, you are given a periodic table here. You will be given the same thing on the test as well, obviously. So you're looking for something that's got 18 electrons in it for a start. So you can see that that would be incorrect. That'd be incorrect as well. It would have to be this one. And, you know, we fill these the way we would always fill them, you know, starting at the bottom, working our way up to the top. When we get to something like 3p, we put, can you all see my cursor here? Little hand, can you all see that?
Yeah.
Okay. So you would do the up arrow, the up arrow, the up arrow, and then the down arrow, the down arrow, and the down arrow, obeying Hund's rule for each of these. And then that would be your answer. All right, so again, you know, it's all practice on these. It can be any of those elements from 1 through 20. Number 12, the full electron configuration for SN2+. So again, I would go back up to the periodic table and work it out. And you don't put any spaces in, I don't think. I think that's what it requires as far as formatting goes. Let's have a look. It does give some directions here. Yeah, put a space in between each subloop, okay. And write superscripts as normal numbers, all right. So you would put a space in between each one, because that's what it's requiring. Now, obviously, if you didn't put a space in and then you got it wrong, you could always email me and say, well, look, I got it right. I just didn't put the spaces in. I'd be okay with that. I'd go in and correct it. But you should just try and follow the directions. So it'd be 1s2, that's for hydrogen and helium. Then 2s2, then 2p6, 3s2, 3p6. That would bring me to argon here, 4s2, that'd be down here for calcium. And then what are we looking for? 10, 2+. So then it would be 3d10, 4p6, and then 5s2. Where's 10? Oh, I can see it. Okay, so 5s2. And then 4d10. And actually that's where I'd stop, because 10 2+ means it's 10 minus 2 electrons. So 10 would be 4p2. But if I chop that out, then it's 10 2+. And that would be my final answer there. Does anybody have any questions about the electron configuration? Now remember, it could be positive or negative. If it's negative, then you'll add electrons. And then you'll do the electron configuration from there. So it's not too bad. Does anybody have any questions? So you get two problems here. could vary between looking for the initial temperature of the metal or the initial temperature of the water. In this case, case number 13, we're looking for the water. I think it's good to draw a little picture. Shows our information. And what we've got here is we know what the mass of the metal is. We know that we're looking for the initial temperature of the water here. So all we know is what the final temperature of the water is, but we'll get to that in a second, and I'll put that over here. That's going to be 27.8 degrees. That's the final temperature. The mass of the water is given to us as well. And that's going to be 189.30 grams. It's obviously not changing. And we also have the initial temperature of the block, which is 219.0 degrees Celsius. Now, the final temperature of the block is going to be the same as the final temperature of the water, which is going to be 27.8 degrees Celsius. So you can see that the temperature of the block has gone down. And that's important information, because if we know the temperature of the block has gone down, it means that the temperature of the water has gone up to 27.8 degrees. Does anybody have any questions? Okay. All right, so let's see what we're doing here. So we need what we need to do is find the heat released by the metal, because that's what we have the most information about. Q equals mc delta T. I can't remember if I include that as a thing. I haven't. All right, I will. I'll add that in. I think I meant to do it last time. All right, so Q equals mc delta T. The M is, and this is for the metal. So Q is mcm delta Tm. Okay. So the mass of the metal is 63.20 grams. The C of the metal is given as being 0.2189 joules per gram per degree Celsius. And the difference in temperature is going to be 219.0 minus 27.8 degrees Celsius. And that's going to give us a figure, and that's going to be in joules. You know, I think it's important to understand the units and to do the units when you do the work. I know the temptation is to just drop the units, but I feel like that's too mechanical. I feel like understanding the units is important. Is there a units quiz for this? I can't remember if I included one in this class or not.
I haven't seen one yet.
You haven't seen one? Okay. I'll go take a look at the end and see if it's there or not. I can't remember if I included it. All right. So that gives me the heat of the metal. Now, what I need to do is realize that the heat absorbed by the water is going to be the same as the heat released by the metal. So we know that QW is equal to MW CW delta T W for the water. We're interested in the change in temperature of the water, which is going to be QW over MW times CW, which is going to be the same as QM, And the mass of the water is 189.30 grams times the heat capacity, which is given as 4.184 joules per gram per degree Celsius, which is going to give me a value in degrees Celsius. Now that's the change in temperature of the water. The initial temperature is going to be 27.8 degrees Celsius minus the degrees Celsius calculated from over here. Now the reason for that is because we know that because the temperature of the metal went down, then the temperature of the water must have gone up, which means initially it would have been less than 27.8 degrees. And that's the thought process I want you to understand. Does anybody have any questions? Nobody has any questions, huh? All right. 14 is a little different. Look at a picture of this. Now we don't know the initial temperature of the metal, that's what we're looking for. We know its mass, which obviously doesn't change. We've got the mass of the water, which doesn't change either. And, you know, we've got also the final temperature of the metal, which is 28.7 degrees Celsius, which is also going to be the final temperature of the water as well. But we also have the initial temperature of the water, which is 22.5 degrees. What does that mean? It means that the temperature of the water went up, which means the temperature of the metal must have gone down. So our first step here is to figure out the heat gained by the water. I know it was gained because the temperature went up. Now let's see, CW. And the temperature difference, which is going to be 28.7 minus 22.5 degrees C, which is going to give me the heat for the water, which happens to be the heat lost by the metal as well. QM is equal to MM CM delta TM. We're looking for delta TM, the change in temperature of the metal, so we can get the initial value of the metal's temperature. And let's see, joules. And the joules here is the same thing as what we calculated for the Q of the water. The mass of the metal, 79.40 grams, times the C of the metal, which is given in the problem, 0.2444 joules per gram per degree Celsius, which again gives us a degrees Celsius difference in the temperature. So the initial temperature of the metal is going to equal whatever we have here, whatever the final temperature was, 28.7 degrees, plus whatever the change was for the metal. And we know it's plus because we knew that the metal would have been higher in temperature initially than it was at the end, because we know that the water went up in temperature, which means the metal must have gone down in temperature. So I hope hope you understand what I mean by that. Does anybody have any questions about number 14? Okay. So for this one, there's two possibilities. I guess they're both here. You can have grams or you can have energy. So for the grams one, we're starting with the energy. And we can see that the energy, oh no, sorry. Yeah, the energy is 7.729 megajoules. And we're trying to figure out how many grams of C would come from that. Now a megajoule is 1 times 10 to the 6 joules, and you can see I have that there. So we've got 1 times 10 to the 6 joules. So that should be the first step, is to convert it to joules. Well, actually, you can do joules. We should do kilojoules. So let's do kilojoules instead. So that'll be 1 times 10 to the 3 kilojoules per megajoule. Now you could do it in 2 steps if you wanted, but you have to end up kilojoules because that's what we have in our equation here. And then we can do how many moles we're expecting, and we know kilojoules are going to be on the bottom here. So kilojoules, that'd be 1930. And I don't include the minus here. And the reason for that is because I want a positive number for grams at the end. And I know that 6 moles of C will provide that. And then it would be the molecular weight, 125.9 grams of C over 1 mole of C. Now remember, C isn't carbon here. C is some sort of fictitious compound. And you know that because the molecular weight isn't the same as carbon. Anyway, that will give you your final answer here in grams of carbon, or grams of C, I should say. Anybody got any questions?
Yeah, what number did you write for 1 times 10 to the blank kilojoules?
3.
3? Okay.
Yeah. But it's the same as this, David. I might not expect you to know what a megajoule was, but I certainly expect you to know what a kilojoule is. But if the other way of doing this is we can do that many megajoules times 1 times 10 to the 6 joules. Whoops, not 6 joules over 1 megajoule. That's the information you're given. And then you can say, well, that would be the same as, let's see, 1 times 10 to the 3 joules over 1 kilojoule. So you can see how that would end up being the same thing. Is that okay?
Yeah, that's fine. That's fine.
All right. So the other one, we've got 1326.8 grams of A. Again, something fictitious. And we want to figure out how many moles of A that we had. So 1 mole of A over the molecular weight, 190.9 grams. And we could figure out how much energy that would give us. It looks like it's 1805 kilojoules. And it would be for 3 moles of A. So by writing it that way, we get the moles of A to cancel. And then we would need to get to megajoules. And as I discussed earlier, the conversion for that would be 1 megajoule is equal to 1 times 10 to the 3 kilojoules. And it gives us the same answer as we started with the megajoules. All right, does anybody have any questions? All right. The last one, so it's about semantics here. It's the possibilities for heat here. It says heat is going to be releasing or absorbing, and the work is done by the system, or work can be done on the system. So those are the things that we're looking for. Delta E is equal to Q plus W. In this case, it's releasing, which means it's going to be negative. And for work is done by the system, so that's going to be negative as well. And that will give us our final answer. But you can have any possible combination of those, and it's going to be 2 places past the decimal for the sig figs as well. And again, if you want more background on that, I don't want to go through a full lesson on this. If you want background on this, go back and watch the lecture where I went through it, or go back and watch the videos for it, the heat and work video. Does anybody have any questions?
This lecture will be uploaded because I missed some of the work on some of the problems.
Yeah, well, yeah, all the. Let me get out of here. The other thing, make sure that you practice with the on-a-lot calculator as well. I've got a link to it here. Because you're not able to use your calculator, your handheld one.
We aren't allowed to use handheld calculators at all?
No.
Okay.
Have you in the past, Emily? I won't ask that. I mean, I can go back and check. That's the thing. So, the thing is, I can't tell the difference between a cell phone and a calculator, and neither can on-a-lock. So it gets flagged usually if you're using a handheld calculator. I make it pretty clear in the syllabus you can't use a handheld calculator for that reason.
Okay.
Now I'm curious. I want to go back and see if you did. Maybe I will. Maybe I won't. I don't know. You don't want to be taking the risk, is my point.
I did have a question though about so you said there was something about like taking extra credit quiz and stuff like that. Which specific ones are extra credit, I guess?
Well, all of these in these folders down here, heat and work. So the enthalpy credit quiz,
Oh,
the
so
enthalpy
those,
from bond energy credit quiz.
so those are all extra credit then.
They're all extra credit. It's not homework, right? This is clear in the syllabus. Okay, there's a bunch of them.
Okay. I was trying to read up on it and like it was kind of confusing me, so that's why I just wanted to verify. Thank you for that.
David, did you watch this video here?
I don't think so.
Well, I tell you what, rather than harass me after class, I want you to watch that video because it does actually go through that algebra.
Oh, that was me.
I'm sorry, who was it?
That was Roland.
Oh, Roland, I apologize, David.
It's
I thought it was I thought it was you who asked me. It was Roland. I'm sorry about that.
and you said that is that in the mid lecture or the mini lectures or where is that?
No, it's
Or
in the
it's
board
transition?
transitions folder where the quizzes are.
So I think I was referring to that video and I was trying to figure it out, and I think you stopped and you said it was all algebra after that.
Oh, I
before
might have. Okay, that's possible.
Yeah,
All right, then. Okay, I'll talk to you after class.
I appreciate that.
Fair enough. Fair enough. All right. So yeah, there's a bunch of them here. You know, bunch of them. All right, there you go. A whole bunch of stuff. Wow. Let me see. I just want to see if there was a units quiz here or not. It doesn't look like it. No, I didn't include a units quiz for this test. Okay. I think I did for test 4 though. Let me take a look. Did I or didn't I? I did. Yes, that's right. That's what I was getting. Yeah, so I didn't include a units quiz for test 3, but there is one for test 4. That's actually part of the test. So I'll be going into that. That's not done on Honor, but that is part of the test. It's worth 10%. You can take it as many times as you like. That's in test 4 though. I didn't do one for test 3. I should at some point, but I thought it's not really. I don't know. Maybe I will. Maybe I won't. But not for this semester. All right. Does anybody have any other test 3 related questions? Any other test 3 related questions? Okay. All right. So Roland, I'll ask you to hang around. I'll go through that algebra. If anybody else wants to see me do that too, you're welcome to stay. Otherwise, I'll see you all next Wednesday. Remember, there won't be class next Monday. Test 3 will be due. I'll be available to help, need be, but people should start studying for it. I think it'd be a really good idea. Don't wait till the last minute to take it. I keep on saying that, but whatever. All right. See you all later.
Have a good day.
All right. See you. All right, Roland. Okay, so let's see. Energy.
I can sort of give you the problem because it gave me wavelength and it gave